Now, following up that, here's my major sections. First, I give an introduction, and then I analyze the swing models, give it a comparison, say something about the future improvement, answer 2 questions, and then draw a conclusion. The main purpose of the lab is to investigate the motion of an object dropped at rest. In my lab, I drop a broader eraser at rest, which means that the initial velocity equal to 0 and the path is strictly downward. I apply Newton's second law here, and the most important thing about the Newton's second law here is the net force. The only difference between the computational model 1 and 2 is whether we consider drag force as a part of the net force or not. Here is my observational model. The mass of the border eraser is 0.02 kilograms, and the height to drop is 2.067 meters. The initial velocity should be 0, so I have to avoid exert a force by hand, so that give it a velocity, and I have to analyze it from the point that it at rest, or else the velocity should not be 0, and the horizontal velocity should also be 0. Here's the tracker model that I built. As you can see in the coordinate system, the origin is right on the point that it is at rest. And on the right is a plot that I have drawn. You can see that the change of the position in every unit of time becomes larger as the time increases, which means that the motion has an accelerating velocity. Here's some data that I have drawn. I have accessed some data from the tracker model and tried to build my computational model. Here is a minor error that the values on the x direction should be all equal to 0, but actually it is not. But it had no effect to our final result because the x-axis will not affect the y-axis when the projectile motion or falling after the motion. Here is my first computational model that I only consider the gravitational force. This is my code here. As you can see that the initial position of velocity ought to be 0, and the acceleration is 0.8. The j hat is pointed vertically upward. Net force is equal to the weight. As I run this code, this is the result that generated. The second computational model, I also have to consider the drag force. We know that drag force prevents the motion of the object, and drag force equal to B multiplied by V squared. B here is a constant that is influenced by many factors and very hard to calculate. So here we have to estimate B by trying different value of B to find the particular value that make the final position as close as to the observed model's final position. Here's a code that I wrote. The only difference between this code and the previous code is that net force is equal to the weight plus the drag force. And this is the result that I run the code. After I have built the 3 models, I make a comparison. First, I compare the model, only consider gravitational force with observational model. We will see that the observational model is slightly above it, which makes sense because when you only consider the gravitational force and not consider the air resistance, it will show that the velocity is much more larger. And the second is that I compare the model consider the drag force and not consider the drag force. We'll see that first they were really perfectly matched with each other, but as time goes on, the model with drag force was slightly above it, which means that the velocity will be smaller, which makes sense because first the velocity is very small and the drag force is not that large. As time went on, the velocity become larger, the drag force become larger. and make the difference become even more larger. And third, I compare the observational model with the model consider the drag force. And I find that the observational model is slightly above the model with drag force, which is not that makes sense, probably because some errors that I have made in the lab. First, the angle when I capturing the video is not really perpendicular to the screen, and the arrows in marking the center of masses could also be happen. Here I answered the two questions. First is which model predict the terminal velocity? I think the model without drag force, because the model with drag force, in order to have the value of the b that we intentionally make the final position matches with the final position of the observation of the model, so that we do not predict the terminal velocity, but we create it. What if we initially threw the object downward? We know that when we drop the object, its velocity is 0, and when we throw the object downward, we give it a velocity so that it will move more faster, so that terminal velocity will be larger. Now that I create a model that I assume that the initial velocity is 0 minus 0, and I created the code there. You see, I changed the velocity, and as I run this code, you will find that the terminal velocity is about twice as large as the velocity that when you drop the object. Here's a conclusion that the computational model roughly corresponds to the observed model, but the errors happens in the lab make the computational model with drag underpredicted the observed model. So I have to make some improvement. First, I have to adjust the angle of the camera, and then I have to drop the object from the higher places that mark more center of mass to make it a much more precise. And then I have to choose a much more suitable object that is either too heavy because it will drop too fast, or too light, it will not drop down. Thank you.